Remember I told you in our last video that when you see a bracket looking this way, it means plane. So in this video we'll be dealing with planes. So as you can see in this first cube, number 1, we have our xyz, x, y, and z, and we have, this is our x, this is our y, and this is our z, right? So here, this is the Miller indices. This number given 100 is the Miller indices. This number 100 is our Miller indices. So we have to get the intercept by doing the reciprocal. And how do we do that? So I think I'll be doing it. Okay, let me do it somewhere here. So getting the reciprocal of this, like I said, 100 is our Miller indices mi. So to get the intercept, to do the reciprocal, it means 100 raised to power minus 1, which means 1 over 1 over 1, 1 over 0, 1 over 0, which means we have 1, infinity, infinity. So this is what we are going to use in taking our reading. Again, this is our x, this is our y, and this is our z. This means it's going to be parallel to y direction, z direction. So I want you to understand this, that if this is our point of origin, remember how we choose our point of origin, always face direction. We are going to the positive side of x. So I know if I choose here, I can always go positive in this direction. And if it was a negative, I will know my origin is supposed to be in front because I'll be going backwards. So I'll erase that now. So now we are being told that we went 1 from the origin. So sometimes always mark your origin with, not sometimes, every time, always mark your origin with 0.30. Then we know we are going 1 on x direction. So it is this. This is a plane and not a direction. If it was the direction, we would have go ahead, drawing our arrow and walking away like nothing ever happened. But since this is a plane and we are being told that x is 0.1, which is parallel to our y and z axis. So this is our y axis, parallel to this place, and parallel to our z axis. So all we do is we trace. So this is our plane. Because it slices on x-axis, on our x line. It slices on our x-axis. So let's look at the second one. Remember, this is our mi, so we have to take the reciprocal, which is 0, 1, 0. Sorry, we have to take the reciprocal, which is 0, 1, 0 inverse. So we have 1 over this, 1 over this, and 1 over this, which leads us to infinity, 1, infinity. This is our point of interception. So now we know if we pick our origin here, we can travel positive on any direction, and we know we are traveling on y direction. Let me do the x, y, and z. So this is our x, this is our y, and this is our z. So traveling on our y direction, we know this is our point, and we know that it is parallel to both our z and our x-axis. So we shade all of this to tell you that this is our plane. I want you to imagine like cutting something. It's like a section, like this is the part that is being sectioned. So this is our plane, right? So the next one, again, we do this is our Miller indices. So we do the inverse, 0, 0, 1. We do the inverse of this, which means 1 over 0, 1 over 0, 1 over 1, which means infinity, infinity, 1, x, y, z. So we close this again. So we know we are traveling positive. So this is our z, y, and x. So since we are traveling positive, we are going on to z direction. That's the only guy that has, and it's parallel to our x and y axis. So we do this. This is the plane that slices on our z axis. So now let's go to question number 4. This is our Miller indices. Remember Miller indices, then we go by doing the reciprocal, which is 1 over 1, 1 over 1, and 1 over 0. So we end up having 1, 1, infinity, right? Then this is our point of origin since everything is positive, and this is our x direction, y direction, and z direction. So it says we are going one on x, y, z. So it says we are going one on x, one on y direction, and it is parallel to our z, so means parallel to our z. This is our z plane, parallel to it. So this is our point. So we can shade like this. Right. So next in line is 101. So Miller indices, we do the reciprocal once again, which is 1 over 1, 1 over 0, 1 over 1, and we have 1 infinity 1. Right. So this is our x, y, and z. So x, y, z. Remember to always put the brackets. So we know we are working with plane. So on our x-axis we have positive, so this is our line. So positive of x is here, then positive of y, I'm sorry, y is not given, it's infinity, so we're gonna be parallel. Then okay, I keep forgetting point of origin, let's just put that. Then for our z, which is this guy, and we know that it is parallel to our y, so which means I dot it here, and this is our square. Right, then let's go again. This is our x, our y, and our z. So we do the reciprocal of our Miller indices, we will end up having infinity 1 1. So we know this is x, y, and z, so we are picking our point of origin here because it's all positive. So this is my y, distance 1. Remember, if we had half, if our indices here was half, right, you would stop somewhere in the half here, somewhere in half here also, you get. But if it was 1 over 3, 1/3 the size, it stops somewhere here. So I'm just going to erase that because we are dealing with whole numbers, we don't have fractions. Sorry, can I erase all of what I did? So back to what we're doing before I diverted. So we have y1 and our z is 1, so it is parallel to our x direction, which means this is the direction of x. It travels towards the direction of x, so this is our plane. Hey, sorry. So travels direction of x once again, then this is our plane. Yeah. Okay, so guys, welcome back again. These are the next questions to do with. So as you can see here, we have triple ones. So remember, this is our Miller indices. So we need to turn them into intercept, point of intercept. And how do we do that? We do inverse of this, which is 1 over 1, 1 over 1, 1 over 1, which basically still takes us back to triple ones, right? So let's pick this as our point of origin, 0 0 0. Then we know this is our x, y, and z axis. So this is our x, y, and z axis. So from the point of origin, we pick our x. we pick our y, then we'll pick our z, and if we connect this together, it gives us this. And we shade our plane out. Right, so let's go for this next guy. Let's do the reciprocal of this, which is going to be 1 over minus 1, right? And we have 1 over 1, and we have 1 over 1, which leads us to minus 1, 1, and 1. So this is now we need to be very tactical because our x is negative, right? So if we pick it here, we'll have to travel backwards, so we have to put it somewhere in front for our origin. So let's count now. So this is our x, y, and z. So for our x, we go -1 backwards. So this is our backwards point on our x plane. And for our y, we go +1. So this is our +1. And on our z, we go, okay, let me mark this as my point of origin. On our z, we go this way. So how do we connect this? So this is our plane. Literally will only be able to see it in front. It's like it's a triangle actually. So in continuation, let's do the reciprocal for this guy also. So we have it to be 1 over 1, 1 over minus 1, and 1 over 1, which leads to 1 based on this. So here we go. We know our y is negative, so we have to be sensitive about that. This is our y plane, right? So since we are traveling backwards, so we have to pick from this point. So let's go by saying x is 1, y is -1, and our z is +1. Z, y, and our x. So if we are drawing this, it's another triangle, which is literally inverted of the last or previous one we drew. Okay, so next for this guy, let's do the inverse. We have it to be 1 over this, 1 over this, and 1 over this guy. So it should be 1, 1, -1. And now we know our z is negative, so we'll have to travel downwards. So whatever we're doing, we should pick the top for our origin. So this is our z, this is our y, and this is our x. So we know from here our x is 1, so we travel 1 forward. This is our origin. And this is our origin. So x is 1, our y is also 1, and our z is a -1. So we draw a plane looking this way. Yeah, that. So now for -1, 0, 1, so we go again, intercept. Why is this looking like a T? Inverse, so we have 1 over -1, 1 over 0, 1 over 1, which leads us to -1, infinity 1. So our x is negative, which tells us we have to put our origin in front somewhere. So we go x, y, and the z. So we go backwards, 0.1. So this is our origin. backwards for 1, then we go infinity on y, then we have z to be, we have z to be 1, so we go infinity towards y, which means it's parallel to this direction, and here is our square or our plane. So for this, remember we are doing the reciprocal of this, which becomes 1 over 1, 1 over negative 2, and we have 1 over 2, right? Which leads us to 1 minus half and the positive half for our x, y, z plane. So this is our x, this is our y, and this is our z. So one thing we know is our y is negative, which means we are traveling backwards, and that advises us to pick our point somewhere here, point of origin from here, so we can always travel negative direction. So from here, our x is positive 1, we have our positive 1 here, then our y is half, so I think half should be somewhere around here, and our z is also half, so half of our z should be somewhere here. So pick our points, draw out our plane. Sorry, this is supposed to be touching this wall. And then, alright guys, there's our plane. Thank you very much, and make sure you subscribe. Feel free to drop a comment if you find something not understanding. So looking at this guy, this is our x, this is our y, and this is our z, right? So it tells us on our x direction we travel 0, on our y direction we travel 0. So it's just going to be z. So let's pick this point as our point of origin. So on our x direction, remember this is our x direction, this is our z direction, and this is our y direction. So on our x direction, it tells us it's traveling 0. On our y direction, it says 0. So we start at our point of origin. Then on our z direction, it tells us it traveled 1 upward. So we know this is our arrowhead, and this is the direction to which it traveled. Remember, on our x direction 0, so we don't move. On our y direction 0, we don't move. But our z direction, it goes this way for a full length 1. So next question, we have 1 by 2, 2. So remember, when we were coming into plane, we are always multiplying by 2 just to cancel out, just to arrive at these, cancel out our halves. So now we want to cancel out back. We do that by multiplying by half, which is equals to opening a bracket. So we have half, and we have negative 1, and we have a positive 1. So remember, when we came from this guy to this guy, we used to multiply by 2, but now we are going from this guy to this guy, so we are multiplying by half. So this is what we are going to use in taking our reading, this guy. So let's pick our point of origin again. Okay, so another thing I need you guys to pay attention to when you're picking your point of origin. So this is our x, y, z. Now we are being told that our y is a negative direction, which means whatever we are doing, I'm coming, if this is our y, if this is our x, and this is our z, so it means whatever we are doing, right, on our y direction, we are going the other way, we are going this direction. So I wouldn't want you to pick this. Imagine I pick this place as my point of origin. Whenever we are traveling on our y direction, we'll have to go like this, which is outside our lattice, our unit cell. So it's just best that I pick my origin at this point, right? So since I'm picking my origin at this point, let me erase this also. Yeah, so since this is our point of origin, on our x direction, since we're traveling half, we go half to the center, we stop here. Then on our y direction, we are being told we are going for a full length. So remember, we are going negative y, so we go this direction, stop at our y. Then on our z direction, they say we are going upwards full length, so we go up on our z direction, positive z. So this is our last point. Then what do? We draw a line from our point of origin to the stop point. So sorry, my line might not be straight. I'm trying our best as possible to make it look straight. Yeah, so that's our reading for this question. So let's go to the next guy. We have, sorry, this is one, it's 311, right? So what do? We know this is our x-axis, y-axis, and z-axis. So our goal now is to cancel out our 3. So we know we have to multiply by 1 over 3, not 1 over 2. Right? Then we click on our equals to sign. And we say 1 over 3 times 3. We have a 1. We have a 1 over 3. And we have a 1 over 3. Then put our direction, sign. Okay, so let's travel. Now for this one, we can put our point of origin at this point. Why? Because we have no negative sign, so everybody's looking all good. So we are told we go, sorry, x, y, z. Sorry, I'm always forgetting to draw my planes because I think I'm familiar with all of them, y and x. So we are being told we have to travel 1 towards our x direction. So we stop here. Then we have to travel 1/3 the length of our y direction. So this is our y. We're going positive y. So we go 1/3 y direction. So I think this is 1 over 3 of my y direction. Yeah, we're not going half. So if I was going half, I think I would stop somewhere here. But no, we are not going half. We're going 1/3. So dividing the length into 3 places. Then we are going 1/3 on z axis. So 1/3 of our z-axis is going to be somewhere drawing this direction. So I should stop here, so I should stop somewhere here. So this is our point. Then picking up the ruler now, I have to draw out our plane, which is this. So arrowhead, this is the reading for this. Now let me raise this direction line so we can see. Yeah, we're raising all of these. That's it, 1/3. 1 on x direction, 1/3 on y direction, and 1/3 on z direction. So for this guy also, we have positive signs. So we are free and good to choose this as our point of origin. So remember, this is our x, this is our y, and this is our z. So if this is our z plane, and this is our y plane, and this is our x direction. Sorry, I keep saying plane, but you should understand I mean direction. So we don't need to expand any bracket here. We don't need to expand any bracket. We are not multiplying through by anything. So we have our figures the way they are meant to be. So in our hex plane, we go forward for 1. We stop here. Says on our y direction, we go 1 also. So we go y this direction. We're good. Then on our z direction, we go upwards. So we know this is where we're stopping. Okay, so I pick up a ruler and I try to draw it out. So it's gonna be this in my arrowhead. So this is our 111 plane, right? Then next in line, we go from point of origin. So we have 0, 1, 3. Here we have to convert. So I'm multiplying all through by 1 over 3 once again. So this is going to be 0. This is going to be 1/3, and this is going to be 1. Right? So from our x-axis, x, y, and z. So this is our x, this is our z, and this is our y. So on our x-axis, no movement, so we keep it there on our point of origin. We stay on our point of origin. Then on our y-axis is positive, so we go 1/3. I think this is enough for my 1/3. Then on our z plane we go totally to the top, so this is here at this point. It's here at this point. So pick up the ruler once again. Pick up the ruler, then connect the dots. So here's our plane. Let me erase this so we can understand our plane well. That's our plane. So here's our direction. I mean, not plane. This is the direction. And let's go for the 101 also. So now remember I said pay attention to the negative sign. So we have x, y, and the z. So we know our x direction is negative. If I had picked this place as our point of origin, I want to go in our x direction, we'll have to draw outside, right? So it is smart to come forward. Whatever axis we're choosing will come in forward, then moving backwards. So I'll be raising this guy. This is my point of origin. So I go x, y, and the z. So now I have to go on my x direction, negative, so full plane. I stop here. On my y direction, I'm going positive, but 0. So I stay at that point 0. I'm not moving. Then on my z direction, positive 1. So that's a full length. I go upwards, upwards, and I stop here. So that means my plane is going to be looking, my direction vector, it's going to be looking this way. So here is my vector. Let me erase all of this. That's that for that guy. Okay, so our y is negative, right? Which means we are going this direction. So if I choose this place for my x, right, in which I go backwards, I have to go this direction, which this place doesn't work. It has proven that. So this place, let's see, if I go this way, it makes sense. I'm inside my cubic, my unit cell. So for my z, I'm going upwards, which means it's literally like this, which makes sense. So I know this point is best for my point of origin. So let's travel now. Negative x here, negative y here, and our positive z goes here. So let's draw out our plane. So this is it for our plane 101. So for the next one, I know my x, I can put my x anywhere. I can either choose this or this for the x direction. So I can come forward on any of these two lanes. So let's check for our y. I have a negative y, which means I'm going backwards. So this guy is best because I could go backwards. If I go backwards in this place, that's awful. So I erase this guy. I know this origin looks best. So for my z, I'm going downwards, which means I'll be going outside. Then what does that prove? It means this is the best point to be my point of origin. So now let's do it. We have our x, positive x direction. Then we have our y, negative y direction. And we have our z, which is a negative z direction. So when I stop here, pick our ruler, then let's draw it from our point of origin. For this guy, I have x, y, z, and x. So let's check again. Our x is negative, which means it has to be in front, one of these two fronts, right? Then our y is positive, which means I have to travel this direction. Then that proves to me that this guy is not useful. This origin is not useful. I just erased it. Sorry. Then for our z, I'm going negative direction, means I'm going down from here. So that proves to me that the best point of origin is up here. So now let's draw it out. So my x, I'm going negative. For my y, I'm going positive. Then for my z, I'm going negative, which leads me to this point. So let's draw. Yeah, so this is it. So let's go to question number 4. Sorry, here is this. Question number 4, we know our x nothing, y something, z something. So y, z, and the x. So if I choose this place as my point of origin, it's okay because I'm going positive y and positive z. So this is my positive y and this is my positive z. I'm just going to erase that now. So on x direction, no movement, so we stay there at the origin. On our y direction, we move. On our z direction, we move. So which means this is our vector. Let me erase this so it doesn't confuse you. Then for our 101, this is x, y, and z. So it means on our, well, I can choose this for my origin. I'm going all positive direction, x, y, and z. So on our hex direction, I'm coming forward. On our y direction, sorry, it's meant to be a zigzag. On our hex direction, I'm coming forward. On our y direction, no movement, so I stay there. Then on our z direction, I'm going upwards. So this is our vector. Then last, I know this is the best place because that's where I can travel positive on all directions. So this is my x, this is my y, and this is my z. So on my x direction, I come forward. On my y direction, I go. Then for our z, 0. So this is our vector. Let me erase this so you know the difference between the vector line and our trace line. Yeah. So thank you very much, guys. Make sure you subscribe. Welcome back to the channel. So first off, I want us to understand how to read directions. So literally everything we are doing here today is all about direction, and this is the sign to which you know it's direction. So I'm just going to put a D here. Then when you see a bracket looking this way, the normal bracket, then you should know this is about plane P. So like I said earlier, we're looking at direction. In this video, we will learn how to identify direction before we begin to learn how to draw out direction. So these are unit cells, 6 unit cells, and we have to like read out their directions. The origin, it went from this place. I'm just going to denote it with 3 zeros, right? Origin, so it originated from this point and went to this point, right? So now I'm going to erase this origin and let's start. So now we want to travel in direction towards where this arrowhead is, right? We want to travel towards the direction where this arrowhead is. So we start from the point of origin, we come here on the point of origin, we draw out that this is our positive x, this is our negative, this is our positive y direction, and upwards here is our positive z direction. So now let's begin to travel towards, we are traveling on the body of this cubic lattice towards the direction of the arrowhead. So let's start by doing that. So we go on x-axis, we know this is negative x, we stop here. So we know we have minus half because it's half, not a full length. So this is a full length. From here to here is 1, right? But since we are traveling from the center backwards, so we'll call that half, and it's on x-axis. So forward this direction is positive, but because we're going in this direction, it has to be negative x, right? So let's erase that again. Let's look at what I just did. Let me erase this also. So remember, I said from the point of origin, our goal is to travel down to the arrowhead. So erasing that again one more time. So let's go again. So we know, okay, from the point of origin, we traveled on x direction, right? So we are going backwards on x. So we have a negative x, right? Then we go on our y direction. We are going against the positive line, so we have a negative, another negative 1y. Remember, it's a full length, it's not an half length. If we had stopped somewhere here in the center, it would be an half, or because it's not in the center, so that's why we call it a full length of y. So now we are not traveling upwards, we are at our junction, so that means our z is 0. Okay, so we might be thinking, why did we not go from here this direction and all? So you can see it's a long journey and it's a very confusing one, because we would have two x figures. We'll have a full x here, one x here, and half an x here, which doesn't make sense, right? So what I do is I went backwards, as I want to travel just once on each direction. So if I had gone forward here, we're traveling twice on x direction, and I don't really know, haven't seen something like that where you have to travel twice on one direction. So here we are not done. Remember, you have to put this sign there, but we are not done. It's half done at this junction. You can't put a minus in front of this, so you go ahead by saying our goal is to cancel these two. We want single numbers. We want to see something like 1110. We want to see something like 111. We want to see something like 011, right? So we need to cancel out the 2 in this answer we just made. So we'll be multiplying through by 2, right? So if I'm multiplying through by 2, we have minus 1 over 2 times 2, comma, we have minus 1 times 2, right? Then we have 0 times 2. So 2 in here, 1, 2 in here, 1. So we have, now let me draw it under here. We have minus 1. Sorry, we have bar 1. We have bar 1, comma. We don't need to put a comma actually. Then minus 1 times 2, we have bar 2. Then 0 times 2, we have 0. So that's the answer for this guy. I'm just going to go ahead and erase all of the stuff we did here, so it can look neat. Yeah, that's that about that. Go back here, come down here and meet him here. So this up here is our z-axis, then this direction is our y-axis, and this direction is our x-axis. So the first thing you should know here is our x-axis, this arrow goes against forward, so we know our x is going to be negative x. Then looking at it, we know our y also is going to be a negative y, and looking at it also, we know our z is also going to be a negative z, because it just goes like against the direction of our positive axis, right? So let's travel. Sorry, let me erase. So I just wanted to erase my arrowhead, they looked really weird. Yeah, so let's travel on our x direction. So traveling in our x direction, so we do this on x, a full travel. So we have our x to be minus 1. Remember, it's going on a negative angle, it's not coming forward. If it was coming forward, that would be a positive, but it was going backwards, so it's negative. So we have minus 1. Then our goal now to travel on y-axis. So this is our y, this is our y line, this line is our y, sorry, this direction is our y again. So now traveling on our y-axis, we go this way, this way, this way, and stop here on our y-axis. So we also have a negative 1. It's not an half journey, it's a full journey, right? So on our z also, now we are traveling downwards to the arrowhead, so we just got to the z, so that's also a negative 1. So negative 1, negative 1. So for this, we don't have to like cancel anything, multiply through to cancel anything. So our answer would be, remember we had negative 1, negative 1, negative 1. So for our plane here, our answer will be bar 1, bar 1, bar 1. Yeah. So let's go to this third plane. Remember, this is our start point. So this is our x, y, and z direction. So looking at this, right? Looking at this, I just know my x is 0. because if I come forward on my x, that is me actually going further away from what's it called? Okay, I think let me do it here so you can see it. This is if I should travel this direction. I'm coming. Let's just assume this is the point. I want to replicate the point here. I don't want the drawing to look rough. So if I should travel forward in this direction, right? That's like a positive x. I'm actually going further away, distanced away from my arrowhead. So the next direction I want to go is my y. So if I go on my y, I go this way. Then if I go on my z, you see, I'm literally going away from my arrowhead, right? So my goal is I'm on the line to which I want to stay at. I'm on the line to which I want to stay at. Like x is already at that point I want it to be. So my x is 0. So see how x is 0, then I want to go on my y-axis. So we are going on the negative y. So we have -1. Then for our z, we are going downwards again. So for the z, we are going on the negative direction. So that's -half. So remember, we would have to multiply through by 2. So remember, we're multiplying all through by 2, right? So 0 times 2, I have 0. -1 times 2, I have bar 2. Then for half times 2, I have bar 1. So closing that up. So here I come, I draw my plane. This is my z. This is my y-axis. Sorry, my drawing now is looking weird. This is my y-axis, and I'm supposed to draw forward, right? But I don't want to draw on this red line, so I'm just gonna come this direction. Let's just understand that that's our x direction. Remember, I don't want to draw it directly on that plane because it's gonna affect our drawing. That's the arrow. So again, what do you think? I know we are coming forward, going leftwards, and coming downwards, right? So here our x is not 0. Remember, we are coming forward, going leftwards, and going downward. Now, the reason why we can't go backwards is because we would be having, if we should go backwards this direction, come leftwards next, then come forward again. That's useless. We are having two x's. So remember, our goal is to have just one reading for every direction. So the best direction to go to is to come forward. So on our x-axis, we know we are traveling positively. So I come here, that's half on my x-axis. So I go this direction. So that's a full journey on my y-axis. So I have negative. Remember, we just traveled against -1. Then on my z direction, I'm traveling against again. So down there, so I have a negative half. So remember, our goal again is to cancel these 2 in all of this equation. I want to have one figure, so it's by multiplying through by 2. So when I multiply through by 2, I have 1 bar 2, and I have bar 1. This is my z, this direction is my y, and this direction is my x. Okay, so traveling on this plane, right? My goal is to get to this arrowhead. So on my x plane, I think from my x plane, I know I'm going this direction, then I'm climbing upwards at the back here. So let me erase that and let's start traveling. So remember, we're traveling against, so we have a -1, right? Then we're traveling this direction. So we have a negative, that's on y. So your goal is to always travel x, y, z axis. You get, when you're traveling x, y, z axis. So you can have like a good reading. So on our y axis, we have a -1 also. Then we are going upwards to z. So that's a positive half. So remember, we are trying to multiply through by 2 just to cancel through all. So we have here our final reading. We have bar 2, then we have bar 2, and we have 1 start point. So I want to travel first on x direction. Okay, let me draw out the plane for people who don't still understand. Sorry. So this is my y, this is my x, and This is my Z. So on my x-axis, remember we have to travel x, y, z. So on my x-plane, I come forward. That's a very positive guy. So 1. So on my y-plane, I go this direction, and I have 1. So I have nothing to do on x-axis, so that's just 0. So this is like a very nice reading to take. And alright, so guys, in this video, I'm going to be showing us how to count the number of atoms in each cubic crystal structure. So right here for number 1, we have the simple cubic. Number 2, we have the body centered cubic. Number 3, we have the FCC. So here, if we count, we have 8 lattice points. 1, 2, 3, 4, 5, 6, 7, 8. So we wouldn't just assume that we have 8 atoms. No, because these atoms are not complete. Now I want you to look at an orange. When I divide an orange into 4, right, the side view of this orange is going to be looking like this. So I'll have it like in four places like this, right? Then I want you to imagine that it was also sliced this way, which means now I have this in 8 places. So that is why you need to put in mind that 1 over 8, every atom you see at each side of the lattice point or the cubic structure is 1 over 8 in size of an atom. It's not an atom, it's not half an atom, it's not quarter, it is 1 over 8. I just explained. If you have an orange divided by 4, we have this shape in 4 places. Then dividing it into half, we have this curve in 8 places. Like, sorry, that drawing looks rough. I think we have something like this. Yeah, half of this. Remember I said it is not 8, it is 1 over 8. So what we do is we say 1 over 8 times how many lattice points do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. So those are 8 atoms on at each lattice point. So that is why we say 1 over 8 times 8 over 1. Why did we say 1 over 8? That's because each atoms are not a complete size. They are divided into 8 equal parts. So we go by saying 8 in year 1, 8 in year 1. 1 times 1 is equals to 1 atom, right? Then for the BCC, we can see that we have a full atom in between the cube. It's like it's pregnant. It's same as a simple cubic, but it is pregnant with 1 atom. So we respect this single atom. We take note of this single atom in the center by multiplying this single and adding this single atom with the summation or our answer from the simple cubic. So we go by saying 1 over 8 times 8. Remember I said we have 8 atoms at each lattice point, but these atoms are not complete atoms. They are divided by 8. So into brackets plus, now we have 1. This guy is a whole atom. This pregnant atom is a whole atom, right? So we are going to multiply it by 1. We have 1 of it multiplied by 1. So we cancel here 8 in year 1, 8 in year 1. So we have 1 plus 1, and that is how the BCC structure has 2 atoms. So let's go to the FCC structure. Here, as you can see, at its faces, we have 6 atoms. It's like a dice. So we have 1, 2, 3, 4, 5, 6. So there's something I want you to take note of. These atoms, now look at this. It was a full, that's every atom we can see on the face. It used to be full, but because it was sliced at this point, sorry, I just erased that. But because it was sliced at this point, so I want you to understand that every atom you are seeing here, they are flat on this surface but rounded in the inner part. So this is what I mean. Inside the cube, it is round, half, but outside here it has been slashed. So literally what just happened is this is what we have inside. We have inside the cube, we have semicircles. So that is why we would respect this by saying we take note of it by saying 1 over 8 times 8. Remember how we got that? It came from our single cubic. It has 8 atoms at its side, plus 1 over 2 times 6. So how did I get the 6? Remember I said this is like a dice. We have a dice has 6 sides. So we have 1, 2, 3, 4, 5, 6. 6 atoms. But this 1 over 2 means half. It is not complete. It used to be complete, but because we sliced, that is why we have half semicircles inside. So that's why we say 1 over 2 times 6. So let's do the math. We have 8 in year 1, 8 in year 1, 2 in year 1, 2 in year 3. So we have 1 plus 3, which is equals to 4 atoms. Thank you very much, guys. Make sure you subscribe to the YouTube channel. Okay, so guys, today we'll be looking at coordination number of structures. As you can see here is the simple cubic unit cell, BCC and FCC. So for the coordination number of single cubic, we know this is 6, we know this is 8, and we know this is 12. Then we know for HCP is also 12. But here I'll be explaining to you how we got to derive all of these. So for the single cubic, we assume that there is an atom in the center, right? Then we have our z-axis, we have our x-axis, or sorry, let me call this the y. We have our y-axis, then we have our x-axis, right? Then we go again, the negative y-axis, the negative z-axis, then the negative x-axis. So as you can see, we have how many in total? 1, 2, 3, 4, 5, 6. So that is how we derive the 6 coordination number for a simple cubic. Now for BCC, we derive it by this atom in the center, which is very straight, pointing to each point or each lattice point in the box. So as you see, if we would count, we have 1, 2, 3, 4, 5, 6, 7, 8. So that is why we have 8 coordination number for the BCC. Then for FCC, which is very, very tactical. Now, for the FCC, we are picking this atom as our central atom, right? So this central atom can point down to just 2 different layers. So this is the first layer, 1, 2, 3, 4, right? Then at the same time, we can point to the lower layer, which is this guy, 1, 2, 3, 4. So the last 4, just imagine we stretch this place up, right? Then we close the box. I want to sketch, sorry. We close the box at the same time. So we repeat these same atoms in the upward manner. We have face, 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 face. That's the 4 walls. You know, this represents 1, 2, 3, 4, 5. Then this is number 6. So it cannot touch down to these down parts. Rather, it will touch again from here. 1, 2, 3, 4. I don't know if that is explanatory. I think I have to redraw that. Let me revert my step. Okay, for a better explanation, I decided to draw it again. So now, like I said earlier, it's like we're placing 2 different cubes on each other. So you can see here I have my 8 lattice for the down square cube, and I have my 8 lattice for the lattice points for the upper cube. Then you can see also I have 5 facing atom, 5 facing atom. So they both share this one central atom. So this is my central atom. I'm going to circle the guy. So now this guy cannot touch this guy. He can't go close to this guy. Neither can he connect to this guy. He can only connect to the side facing atoms and the lattice points that are on his own layer. So now I'm going to be connecting them, and we have to count 12 together. 1, 2, 3, 4, 5, 6, 7, 8. Remember, I said it cannot get down here. It can't get to this down part. No. So it goes again to the side facing atoms. 1, 2, 3, 4. Remember, I said he cannot connect to this guy and this guy because they are way far away from him. Thank you very much. And that is how we have 12 coordination number for the FCC. Same thing goes for the HCP. Let's draw that of the HCP now. Okay, so in continuation, here's the HCP. Let me write it here, HCP. Then let me change my ink, sorry, changing it to red. So the same thing goes here also. We can count how many atoms: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So to count our coordinating number of atoms in this structure, we scroll up again, we repeat the same direction. Remember I said this is the center for me, right? So this guy cannot get down here, so I have to replicate what is down here in this upper part also. So I'm just going to make it look short. I'll make it look short as, yeah. So these are my lattice points, the 6 top lattice points, and this is the triangle in the center with the 3 atoms. Yeah, that's nice. So to count, this is my center. Remember I said it only goes to the 2 layers. It goes 3 layers. That's his own layer, the layer above, and the layer beneath. So let's count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So that is why I said both FCC and HCP, they have both 12 atoms for the coordinating numbers. Thank you very much, guys, and make sure you subscribe to the YouTube channel. This video will be calculating the atomic packing factor of both for simple cubic, BCC, and FCC. So remember in our previous video, I calculated to tell us the number of atoms. We have 1 atom, we have 2 atoms, and we have 4 atoms. Then for the coordination number, we have 6, we have 8, and we have 12. Just for recap, in case you never watched that video, I'm just gonna take it very quick. So as you can see, we have 8 atoms at the each lattice point. So these atoms are not complete atoms. It's 1/8 over 1/8 times 8. So that's how we got 1 atom. Here we have a single atom in the center, which is 1 times 1, which is 1, plus the summation from our simple cubic, we gave us 2 atoms. Then for the FCC, we have facing atoms. Remember I said these atoms on each faces, they are not a full circle. They aren't something like they're actually slashed. They are semicircles, right? So that's why I said it is the formula for this simple cubic 1/8 times 8 close bracket addition of 1/2 times 6. We have 6 atoms on 6 sides like a dice. Then 1/2, because it is semicircle, not a full atom. Remember this guy was a full atom. That's why we did 1 times 1. BCC has a pregnant atom in between. That was why we did 1 times 1. In case this is too fast, you should go back to watch the previous video where I explained it in a better manner. So doing this math, we have 3, 1, which is 3 plus 1, we have 4. For the coordination number, remember I said this is our central point, right? Then we stretch it Z, positive Z, negative Z, positive Y, negative Y, positive X, negative X. So that's 1, 2, 3, 4, 5, and 6. So I'll be raising that now. Then for our BCC, which is very simple, this guy is in the center, so we stretch him to every lattice point: 1, 2, 3, the one behind that we can't see, 4, 5, 6, 7, 8. So that is why we have 8. Sorry, bad handwriting. 8. So for this, remember I said you replicate a drawing, after drawing the cubic, after drawing this, you replicate it again at the top, right? So this is our center. Then this guy will stretch to each lattice point. We have 4 here. Then we have 4 sides. and another 4 side at the top, so that's how it became 12. Just please watch the video on my channel where I did a better explanation to all of those. Here we have 52% for our final answer. Here we have 68% for our final answer, and here we have 72% for our final answer. Now let's go into the calculation. I'll be deleting all of this. Now let me draw a face of this single cubic. Sorry, I keep saying single structure. It's something like this. So remember, this is a radius. Like when we draw a circle, this is the diameter, but the center to the other end is a radius, right? So that is why we'll be calling this a radius, and this is also a radius. So we'll see our A is equals to 2 radius. A is equals to 2r for the single cubic, right? Then for the BCC structure, we have an atom in the center here, right? So now we are considering this diagonal and this diagonal. So this, let me change my ink so I can highlight well what points we're concentrating on in this diagram. Black ink. So this is the triangle to which we are much more interested in knowing the length of each sides, right? But then we don't know this guy. We know this guy. We don't know this guy. We don't know this guy. We don't know the length. So we need to find each length, like in for various parts. So let's start solving by redrawing things in a very better manner. So let's pick this down floor, like this down segment. So we want to find this length for this diagonal. So we draw it out, a flat surface, right? So we have this, and this. So we have the pregnant atom, which is double r's. We have r and r because it's a diameter. Then for here we have 1 r. Then for here also we have 1 r. That is how we derived 4 r's, right? Since I have this space, so here I have 2 r's. Remember, for square, all sides are equal. So if this is 2 r's, the 2 r's, remember we said 2 r's is equal to 1 a. 2 r is equals to a. That's our total length here, is a. Okay, let's call our diagonal b, right? So we apply our Pythagoras theory where we say a square plus a square. Remember we have, sorry, let me erase this. This is it. This is in the 4r. The 4r is this diagonal, but this is also r and r, which derives another a. So that's why I say a square plus a square is equals to b square, whereby our b square is okay, let's denote it by original. What is there? We have 4r square. 4r into square is equals to a square plus a square, right? Sorry, I just switched things around. So I have 4 times 4, which is 16 r square equals to 2a square. Then we divide both sides by 2. 2 in here, 1 in here, 8. 2 in here, 1 in here, 1. So we have a is equals to root 8r square, which is also a, is equal to 2r root 2. So this is this diagonal. We just found this diagonal. So let me note it out here. This diagonal is equals to 2r root 2. A is equals to 2r root 2. Okay, so let's call this angle this diagonal that we just found, let's call it B, right? And this is A. So I think I'll try drawing it out by making it look like this. So we have a diagonal, right? So this is our B is equals to 2r root 2. and this is our A. Remember, we have an atom here and an atom here, which is R and R. So the total distance is A. Then here we have the pregnant atom, right? So we have double R's. This is also a radius, and here we also have a radius. So for this total length, we have 4R, right? Then B and A. Now we need to find this diagonal, like the length. So we go ahead by saying, remember I denoted it as D, so we say D square is equals to A square plus B square. So we need to remind ourselves that our B square is to be equals to A square plus A square. If you remember from our first equation when we derived this, B square is to be A square plus A square. So we bring that into the equation. So we have our 4R into square equals to A square plus, now we are bringing this guy in, A square plus A square. So 4R times this, we have 16R square is equals to 3A square. So we divide both sides by 3 here 1, 3 here 1. So we have our A is equal to root of 16R square, 16R square over 3, which denotes down to 4R over root 3. So finally we found our D, which is equals to 4R over root 3. So I'll be raising all of this. So here we know our A is equals to 4R over root 3. So for this guy, I think we don't really need to solve. Remember I said an atom on the face, then we have radius and another radius. So again, it's 4R's. So we have double R, and R. Then we have our remember my drawing is always bad, so we have an R here and an R here. So if this is A, this is also an A, because all sides of a square is equal. So we apply Pythagoras theorem again, B square D. So our B square is going to be 4R square into square equals to A square plus A square. We know where this is going to lead to. It takes us down to A is equals to 2R root 2. So this is for FCC. We want to look for the APF as atomic packing factor. So we know that APF is equals to volume of atoms over volume of cube, or however your textbook defines it. So for the simple cubic, right? So we know it is remember we said this guy has one atom. This guy has 2 atoms. This guy has 4 atoms. Yeah, and the C coordination number for this guy is 6. Coordination number for this guy is 8. Coordination number for this guy is 12. So next up, we want to look for the APF of this simple cubic. So we go by saying number of atom 1 times the volume of atom, which is 4 over 4, let me erase and write better, which is 4 over 3 pi r cube, right, over our A. So we need to expand this by saying we have 1 times 4 over 3. Let me erase that, please. 4 over 3 pi r cube over our a, which is this 2r, sorry, it is a cube, so we have 2r into cube, right, which becomes 1 times that becomes itself 4 over 3 pi r cube over 8r cube. So r cancel r. So if you input this into your calculator, you should have 0.5236, then times 100, 1 2, so I have 52% for this guy. APF equals to 52%. So I'm gonna be raising all of this. Now let's go to the BCC. So for BCC, remember, is the same thing. We say APF is equal to number of atoms, which is 2, times 4 over 3 pi r cube, pi r cube over our a, which is 4r over root 3, or raised to power 3. Or better still, let me place this r outside here so it doesn't cause confusion. 2 times 4 times 1 over 3 pi r cube, r cube over 4 over 3, cube times r cube. So my r cube can cancel this. Then when you input all of this into your calculator, you should have 0.6802, then times 100, it goes 1 2, then I'm back to my 68%. So you do the same thing for this guy. Remember, it is equal to, we have 4 times 4 over 3 pi r cube over, open brackets, we have 2r root 2 cube, right? So you can do the same thing we did here, which was 4 times 4 times 1 over 3 pi, then r cube over 2 root 2 cube times r cube, so r cancels r, then your final answer should be 74%. Now go ahead, erase all of this and just write this 74%. Yeah, that's all for it. And notice it's all in volume. Hey guys, welcome back to the YouTube channel. So in this video, I'm gonna be showing us how to convert the three three coordinates. When you have coordinates like this, how to convert it to something that looks probably like this. But all I just want you to understand is how to go from these Miller indices to Miller-Bravais indices. Yeah, so let's dive into the video. Make sure to like, comment, and subscribe to the YouTube channel. Thanks and bye. So first off, in this video, I'll be giving formulas to which you use to convert from these to these. So first off, to find out u, the formula we use is n over 3, open bracket, 2 u prime or u initial minus v initial, right? Then formula for V is same thing, but we just tweaked a few things. 2V initial minus U initial, and we have our T to be minus open bracket U plus V. Then we have our W to be N times our W initial. Sorry, I didn't close these brackets. Then on the other hand, for HKL to HKIL, all we are concerned about is the high. We're concerned about the high. So formula for looking for our high, every other coordinate remains the same. So just find your high. Our formula to find your high is equals to minus open brackets H plus K. So we'll be solving few questions, and we'll be solving one question applying both for plane and direction. Also, I want you to take notes that N is equal to, for example, if we had 1 1 1, our N is equal to 3. N is equal to, if we had 1 1 1 1 or 4 digits, it's going to be equal to 4. Yeah, so let's make use of all of this formula in some example. Okay, so first off, we'll be doing for that of this 0 0 1, and we'll be doing for 1 1 0. Then at the same time we'll be doing for 0 0 1, plane 1 plane 1 1 0. So applying the formula, remember for this 0 0 1, this is our U, this is our V, and this is our W. So we put just this sign above to know that's our initial, right? So we are trying to go from this to U, V, T, W, sorry, direction sign. So remember the formula to find our U is equals to N over 3, open bracket, 2U initial minus V initial, then close the bracket. So here we know our N is equals to 3. Therefore, we have 3 over 3, open bracket, 2, open bracket, our U, which is 0, minus our V, which is 0 also. Then we'll close our bracket and find our answer. So this, in this, we have 1, 1, open bracket, 2 times 0 is 0, then minus 0, so we have 0 here, and total of 0 for our U. U is equals to 0, so let's write it out here. We have our U to be 0. Then formula for our V is equals to N over 3. Then we have 2V initial minus U initial, close bracket, so therefore we have 3 over 3 again, and we have open brackets, 2 open bracket, I think, yeah, they're both zeros again, 0 minus 0 equal to 1 minus 0 equal to 0 again. So we have another 0 for our V. Then formula for our T is minus U plus V, right? So we go ahead, therefore our T is equals to negative of our U, which is 0, plus 0, which is like a negative 0, which is equals to 0. Then we have our T again to be 0. Then for our W, which says N times W initial, therefore we have our N to be 3, and our W is 1, so we have equals to 3, so we have this to be 0 0 3. Then let's divide this. For our HKL, we have it to 0 0 1. Remember, we are concerned about just the height, right? So we know our h will remain 0, k will remain 0, our L will remain 1. So all we are concerned about is looking for the number that stays right in this position. So remember the formula for our high is equals to minus h plus k in the bracket. So here we have our minus in bracket, our h is 0 and our k is also 0. So again we are back to minus 0, which is equals to 0. So we have this to be for our plane and this to be for our direction. So let's erase this again. So we've done both of these. Now we are going for this guy and this guy. So we have again ourselves, we have the u, v, w for direction. We have our 1, 1, 0, it was the bracket, right? So finding our u, we're trying to get our u, v, t, and w. So our u is equal to n over 3, open bracket 2u initial minus v initial, sorry, excuse me, minus v initial, close the bracket. So we go ahead here, also our n is equal to 3 because we got 1, 2, 3, so n is equal to 3. So we have 3 over 3, open bracket 2, our u is 1 and our v is also 1, so it goes our bracket. So we have this cancel this, so it's equal to 1, open bracket 1. That's 2 times 1 is 2, minus 1, that's 1, so we have our answer to be 1. So this guy is 1. Then we go again for our v, which is n over 3, open bracket 2v initial minus u initial equal to 3 over 3, open bracket 2, open bracket 1, open bracket 1. I'm substituting the value of this into my equation. And then I close this and I say equal to 1 times 1 again equal to 1. Remember this cancel 1, that's like this 1. Then this bracket also comes out with 1, so I have 1 again, which is 1 here. Now let's go for our t, which is equal to minus u plus v into bracket, so which is equal to minus of our u and v, which is 1 plus 1, and I have it to be equal to minus 2. So here I place in my bar 2. Then for our w, which is equal to n times w initial, yeah, always have the for initial, which is equal to our n is 3 times our w in this equation is 0, which is equal to 0, and falls back to 0. Then for our hkl, which is going to be 1, 1, 0, 1 will have our h, excuse me, so 1 will have our h, k, high, l. So we'll go ahead and remember all we are concerned about is our high. So our high says its formula is minus h plus k, right? Then we go ahead and say minus what's our h, 1 plus 1, and it's equals to minus 2. Then here we have ourselves part 2. Thanks guys, and make sure you subscribe to the YouTube channel. Alright guys, welcome back. So we're going to be looking for the planar density for FCC structure with plane 111. So first off, we need to know the formula for planar density, which is number of atoms on a plane over area of a plane. So first off, we are looking at FCC and we are being given the coordinate of our plane as 111. So we know if this is our origin This is our 1 on x direction, 1 on y direction, and 1 on z direction. So that is why we traced out that triangle. So we know that on each faces here we have an atom. There's an atom here. There's one here on this wall where this guy is passing because it is face center cubic. So there's always atom on each face. So there's one more atom here. So having this, we bring out our drawing, which will appear this way. Circle, circle, circle. Those are the atoms leaning on the walls. Then we have another atom here. We have another atom here, and we have another atom here. These are the atoms that are on the face centered part of each of our walls. So to know the distance of each side, right, what we have to do is we need to take one face, which is like, since each of our faces, this is how the line travels through, right? On each of our surfaces as phase 1, phase 2, phase 3. So it's like we cut out just one flat box and our line is going this way. So what we don't know is this line, right? But we know that this place is A and this place is also A. So we apply, sorry, let me erase this. So this is our unknown. Knowing that both sides are, we use the Pythagoras theorem, which is like our unknown. Let's use question mark square is equals to a square plus a square. So question mark is equals to root a square plus a square. That's gonna be 2a square. So question mark is equals to root 2 dot a. So this is for every line. So we know that this place is root 2a, root 2a, because all sides are equal. It's an equilateral triangle. So let's erase this. Okay, so now we need to look for the number of atoms. So we have 3 atoms sitting on this place, but like we don't have the full atoms. So first off, we need to know that a triangle is equals to 180 degrees, and we have 3 angles. We hold the 3 angles, so we say 180 divided by 3, which is equals to 60. Then a full circle has 360 degrees, so we say 60 over 360, 0 cancel 0, 1 in year 1 in year 6, so it's equals to 1 over 6, which means that every angle as the edges here is 1 over 6. We own just 1 over 6 the portion, not 6 over. If it was 6 over 6, we own 1, but we own just 1 over 6. So let's erase. To get the number of atoms at each angle, so 1 over 6 times 3 angles plus these guys are half, 1 over 2. They are also 3 in numbers. So 3 in year 1 in year 2, which is equal to 2 atoms. You can punch that into your calculator. We have 2 atoms. Then for the area of a triangle or a rectangle triangle is half base times height. So we have to divide it into 2 to look for our height, since we don't know our height but we know our base. So we'll bring out a triangle that looks just like this. So we know this is going to be root 2a over 2, and this is going to be root 2 dot a, but this place is unknown for our height, right? So let's erase this. Okay, so to look for our unknown side, we know we have to apply Pythagoras theorem, which is root 2 dot a square is equal to unknown square plus root 2 dot a over 2 square, right? So we go ahead by saying unknown square is equal to root 2 dot a close bracket square minus root 2 over 2 dot a raised to power 2, right? So unknown is equal to, if you square this, we have 2 root 2 times 2 root 2 gives us 2, a times a gives us a square, then minus this will give us a square over 2. Punch into your calculator, root 2 over 2 gives you 1 over 2, so which is our a square over 2. Then now let's look for the LCM, because they have like terms. So we have 2, 1 in here, 2 times this, we have 4a square, 4a square, then minus a square, so which is equal to 3a square over 2. So this is simplified enough for us to continue. So we have question mark square is equal to 3a square over 2. So question mark is equal to root 3a square over 2, which lands us to an equation that looks like this. A is going to take care of itself, right? Our A will take care of itself. Then we'll have root 3 over root 2 times root 2 over root 2, which will give us root 6 over 2a. So unknown is equals to root 6 over 2 times a. That's our unknown. Is root 6 dot a over 2. So let's erase all of this. Now let's look for our planar density for plane 111, which is equals to number of atom is 2 over the area, which is 1 over 2 times base, which is our 2 root 2 dot a, times our height, which is root 6 over 2 dot a. So do you remember this thing where we have 1 over 2 over 3, which becomes 1 over 1 times 3 over 2, right? So we're going to apply that somewhere around here now. Yeah, so let's go ahead by saying 2 divided, okay, not to be too fast, we have 2 divided by 1 over 2 times root 2 dot a times root 6 over 2 dot a. Sorry, I just want to make sure I write that way. Root 6 dot a over 3. So therefore we go ahead and say 2 times 2 over 1 times 1 over root 2 dot a times 2 over root 6 dot a. So above we have 2 times 2 times 2, which is 8 over root 2 times root 6 should give us 2 root 3. 8 times 8 should give us 8 square. So if you punch in your calculator, 8 divided by 2 root 3, you should have 2.309 over a square. So therefore the planar density for FCC structure 111 is equal to 2.309 a square. So we have this to be the answer. Okay, so now we want to look for planar density for FCC structure plane 110. So first off, let's draw out our plane. So we know this is our point of origin because there's no negative. So we have it to be 1, 1, infinity. So we have 1 on x, we stop here, and we have 1 on y. So they go infinity towards z direction. So we have it to be this way, close it, and close it. So if you see here, we have an atom at the top and at the bottom here, then we have each atoms on each edges. So let's bring out our drawing. We bring it out and it looks just like this. Looks like a rectangle. So we have a big atom lying here, a big atom lying here, a big atom lying here, a big atom here, and we join this together, join this together, and we know that the height is a, then this is also an hypotenuse. So remember what we did where we found out that it is root 2 dot a, because it's an hypotenuse, it's not like a normal height. Like if it was this line, we would have used a, but because it's not that line, it's an hypotenuse for the base, so we call it root 2 times a. So now let's go ahead by solving. So we know we need area of the plane and we also need the number of atoms. So to get the number of atoms, yeah, this is angle 90, angle 90, angle 90, angle 90. So we say 90 over 360, 0 cancel 0, 9 in here, 1, 9 in here, 4, which is equals to 1 over 4, which means for every circle, we own 1/4 the size of an atom at that angle. So let's go ahead by solving. We have 1 over 4 times how many? We have times 4. Then we have 1 over 2 plus 1 over 2 times 2. So 2 in year 1, in year 1 we have 1 from F1 in year 1, in year 1. So we have 1 plus 1, which is equal to 2 atoms. So let's write it somewhere, 2 atoms. So now we look for the area, which is length times breadth. Planar density says number of atom. Planar density for 110 is equal to number of atom, which is 2 over length times breadth. We have A times our root 2 dot A, 2 over 2 root, that's root 2 A square. So multiply both sides by root 2 over root 2. So when we punch down into our calculator, root 2 times root 2 gives us 2. So we have 2A square over 2 root 2. So 2 cancels 2. Therefore, our planar density for 110 is equals to root 2 over A square. So this guy is equals to root 2 over A square. So and for the last guy, which is 100, sorry, let's erase this, which is the same thing as 1 infinity infinity. So we'll go ahead by drawing out our square. This time around it's a square but not a rectangle. So we do this and we put this guy in the center. So we know that all sides are equal. We have A's all through. Then number of atoms is equals to the same thing, 1 over 4 times 4 plus 1. So it is 1 plus 1, which is equal to 2 atoms.